Hey everyone, welcome to another video. Today we're just going to be doing a continuation of the Laplace transform lesson. So I'll just call this one the Laplace transform part 2. Hopefully you guys enjoy the colors that I'm using here. I think it looks nice. So basically, all we're going to do here is just derive the expressions for the Fourier transforms of sine of AT and cosine of AT, where A is just going to be any constant, right? Um, so find the Laplace transform when f of t equals sine of A times t, and then when f of t equals the cosine of A times t, where A is just a constant. A is defined as some constant. I'm going to do the same thing that we did in the last video, except this time we're not going to use the tabular method. You can see that if we do that, our derivatives never end, and then we just end up adding infinite amount of terms, since the derivatives successively for sine and cosine are cyclical, and then e to the negative st, that derivative never goes to zero either. So no matter how many times we take it. So the tabular method won't work. So what we're going to do is we're going to have to, let me write this out so you can see. So what we're doing is first the Laplace transform of the sine function of at, and we know our integral expression here, so 0 to infinity of e to the negative st times sine of at dt. And what we're going to do is just let this equal I. Okay, so this integral right here is going to be equal to I. Now we're going to have to use the integration by parts formula. There's one really cool way that I saw somebody else use this mnemonic device, but it's that u dv is equal to ultraviolet super voodoo. I really like that mnemonic device. It's always stuck with me. Everybody that I've told it to has said I've never forgotten that. You can also just derive the formula every time as well. But I like mnemonic devices, so it just makes everything a little bit faster. Anyway, when we do the integration by parts for such an integrand, we are going to choose u such that it equals sine of at, right? And then we'll choose our dv as e to the negative st dt. And this means that then du is going to be equal to a cosine at with respect to t, differential dt. And also then finally v, well, that's just the integral of this, right? So that just equals the integral of e to the negative st dt, which quickly evaluates to be negative 1 over s e to the negative st. All right, bear with me. So we've got our u's and our v's. What we can say now is that I, remember our integral up here circled in green, and then we have another integral. Let's define this one now, this integral as being j. Call it j. Don't forget my bounds. Notice I'm not including that constant out front, the a divided by s. We're just concerned with the integral and the integrand within it. Applying integration by parts again, I'm just going to do this really quick since we just did this. We'll say that dv equals the other function, right? The exponential function. Taking the derivative here, we just get, remember the negative sign for the derivative of cosine, right? And also v, we just did that integral above negative 1 over s times e to the negative st, right? Okay. The next thing we want to do is identify that what j is here. So we have this huge expression. Let us solve it for j. Yes, and a divided by s times e to the negative st sine of at. Does this look familiar? Does this integral look familiar? Oh, look at that. This happens to be capital I. And so we can actually just replace, I don't want to write this all again, but I will. It's good to write your stuff a lot too, because then you're kind of like printing all of the details of the problem on the surface of your brain, right? So you just get to know the problem more intimately, and then you're less likely to look over something on accident later. All right, so now that I've recast it that way, we basically can then substitute this back into the first result. So that's going to be putting that back in. We say that I equals e to the negative st sine of at over, and I believe this is negative, yes, s minus, plus a over s times negative, right? And that's why I was saying minus, but we're not going to do that yet. We'll do that in the next step where we distribute. It's really good to just keep doing everything one step at a time. Try not to skip steps in this. It can be deceivingly tempting to skip steps because it does feel good, like when you do some awesome algebra magic that looks super technical, especially if people are watching. So I'm just going to distribute here. But it's important to not skip steps for these types of problems. It gets kind of hairy sometimes, and doing that will just cost you more time. I'm going to distribute this a into the parentheses. No big deal, really, and the negative as well, right? Over, so the s also distributes in. We have squared and minus a squared over s squared I. Okay, so if I move the remember this is I, and so what I'm going to do is I'm just going to add, let's do this in a different color so we can see it very clearly. I'm going to add this to both sides, so this factor times I to both sides of the equation here. And what we end up with is I plus a squared over s squared I, which equals, then again, just this right here. I'm not gonna waste everyone's time. Okay. And what I can do now is on the left-hand side of the equation, I'm going to factor out an I, and this will allow me to like divide through and solve for I. So this is I times 1 plus a squared over s squared. Okay. Man, again, same right-hand side expression. And so what I can do now on the right-hand side is I can factor out a negative e to the negative st divided by the s. S squared. Let me just start writing stuff. I'm thinking too much about this. yeah, okay. So oh, and I also can get a, for this expression here, I can get a common denominator. So I can write these two terms. So I can say that 1 plus a squared over s squared is actually equal to, let's just multiply by s squared. Let's see, what do I have to do to get the same denominator here? What do I have to do? I have to have an s squared up here. So this is just the same thing as s squared over s squared, right? That equals 1. So if I say s squared over s squared plus a squared over s squared, and then we have common denominators, so we can just combine into one fraction, right? And so that means that we actually have I times s squared plus a squared over s squared. Holy cow, we're almost done. And then factoring out the right side here, I'm just going to factor out a negative e to the negative st over s squared. And that will leave us with s on top times sine of at and then plus a times cosine at. Yes. Okay. Close parentheses. Now I can just divide both sides by this s squared plus a squared over s squared. And really what that does is it's just like multiplying this whole thing by the reciprocal of this, right? Which actually looks like it just gets rid of this s squared. And then this part is going to go on the bottom. S squared plus a squared. And so what we have then is, this algebra is pretty heavy, so I'm going to do the same thing for cosine as well, but we'll go much faster on that one. So yeah, if I just rewrite this, so we have negative e to the negative st divided by s squared plus a squared, and then times what is inside this Okay, yes. So I remember we defined that way up here as being this. All we have to do now to solve for it is take the antiderivative, which we actually just did that. Okay, and I think now is the time where we can apply the bounds of the integral on this, right? So we basically found the integral. That is and then I'll apply the bounds here. So evaluating the upper limit for this, we'll just say, and I'll do this the correct way, the limit as t goes to positive infinity for the expression negative e to the negative st divided by s squared plus a squared times s times sine at plus a times cosine at, blah, blah, blah. I didn't even really need to write that whole thing because we know that this term goes to 0, which makes this whole thing go to 0. So that's the upper limit is 0. What's the lower limit? Well, when t equals 0, we have negative e to the negative s times 0 over s squared plus a squared. And then we have times s times sine of 0 plus a cosine of 0 . All right, and let's just start crossing stuff out here. So e to the 0, that's 1. Sine of 0 is 0. A cosine of 0, well, cosine of 0 is 1, so we keep this a here. That term's away. And it looks like we're going to end up getting a divided by s squared plus a squared. And so that's going to equal the Laplace transform when f of t equals sine at. All right, now let's go through the cosine example as well. Very similar. So now that we have kind of all of the math worked out, we can just get moving here. So I'll say, what is the Laplace transform of the function cosine at? All right, well, same situation. We just apply our integral here, and we're going to use the function cosine of a times t and integrate with respect to t from 0 to infinity. We're going to let this equal j. So this is j. And then we're going to use our integration by parts formula. Should be familiar with this now that I gave you a mnemonic device. Ultraviolet, super, voodoo, right? Okay, and for that we are just going to choose that u equals cosine of at, and then we choose our dv as the other function, right? That's the rule. That's kind of the procedure that we use for integration by parts. Du, that gives us negative a sine at, right? So the respect to t is like that, but then if we multiply through by dt, we end up getting this. And similarly, as in the last one, we just integrate dv to get the v, which is negative 1 over s e to the negative st. All right. Now, that means that j is equal to uv, right? So uv minus v du. So u times v minus the integral of v du. V du. Let's call this I. And let's do integration by parts on it again. We actually did this in the previous one, but just for the sake of being complete, I will quickly do this. And therefore, remember j is e to the negative cosine a of t integral. So that's what I'm going to substitute back in right now. Sorry, j is the cosine one, right? Yes. Yeah, that's correct. Oh, I switched the order that I used the I and the j in. That's why I'm kind of confused right now. But okay, this is making sense. And we basically can just distribute again as we did before. No, how do I get rid of that? We have a plus sign there this time, though, I noticed. And then so we're basically just going to subtract this here, actually after the distribution of this is negative, so we're going to add this to the other side. I'm just going to factor out the j also, and we'll have 1 plus a squared over s squared equals this. And then factoring out the right-hand side and dividing through will give us, dividing through by this term, sorry, I should make that clear. Dividing through by this term and factoring the e to the negative st over s ends up giving us this expression here for j. And so basically this is the integral that is j. This means that the Laplace transform of cosine of at equals e to the negative st divided by square root of the sum of the squares of s and a times negative s times cosine at plus a sine at. Yes, okay. And we basically can just evaluate the upper limit by taking the limit as t goes to positive infinity of e to the negative st s squared plus a squared times all of that. It doesn't matter because e to the negative st as t goes to positive infinity is just going to go to 0, which makes that 0, which makes this 0, which just means that the upper limit is 0. Okay, now for the lower limit, let's say when t equals 0, right, because the integral is from 0 to infinity, we evaluated that upper bound to be equal to 0. However, when t equals 0, in this expression, we end up getting a, so if that's 0, that means that that is 1. What's cosine of 0? It's 1. What is sine of 0? It's 0. So that term goes completely away. We're left with the negative s right here times 1. So negative s divided by s squared plus a is what I'm getting here. So that's yeah, negative s over s squared plus a. But remember, we evaluated that upper limit to be 0, so we come in here with the 0 minus the negative, that cancels, and that just equals positive s over s squared plus a squared, which is the Laplace transform for the function cosine at. And that wraps this video up. So kind of a lot of heavy algebra and, you know, some trig stuff, but nothing we can't handle. So I hope you enjoyed the video. Please like and subscribe, and in the comments let me know if there's anything you'd like me to clarify. Also, Let me know in the comments if there's anything that you would like me to cover in the future, and I would be happy to oblige. Have a wonderful day.